Good afternoon, good evening, everyone. Welcome to week 6 of nptel analog communication class. So, today we will be doing voltage control oscillator VCO, and we will be doing phase lock loop, and we will be doing voltage control oscillator, phase lock loop, and costless loop. So, today's topic is VCO and PLL primarily, and this is the week 6 of the problem solving session. So we will start. First, we need to learn what is a voltage controlled oscillator, and so a voltage controlled oscillator is something. Hi, yeah, 30,000 episode will take few hours. 3 hours.
No, actually, yeah, it takes some time. Now we have two options. One is direction and the other direction. So that's why I need to run 10 days of checking.
Even 30,000 will take 3 4 hours.
Because when I kept the 100 like that, 1.6 like that, it take 2 days. I checked on some Sunday, I checked on Monday.
Nah, it's those two computers are running 30,000. So all four remote units. Huh?
Kept all the four in only one program.
Huh?
Separately.
Separate. I made copies, or else if I change one here, it gets changed there.
Okay.
Understood? Like I change here, next I go to change it again, it automatically comes back. So it's not possible to have four variable values together in the same. Then we have to write a for loop. So instead of writing a for loop, I just make 3 copies and add for 3 different types. Yeah. Okay.
But whatever the clock we got, up to 10 to 20 to 4, it is but you say that is good.
Yeah, cumulative reward is more intuitive.
Where I think
Yeah. So today's topic is voltage control oscillator, and yeah, so voltage control oscillator is something whose an oscillator circuit, electronic oscillator circuit, whose frequency can be controlled by the voltage input. So by giving an input voltage, you can directly control the frequency of oscillation of the output. So for VCO, frequency of the output F out is directly a function of some function G of the input voltage. So this is the characteristic function of a VCO. Now for this VCO, for this VCO, we will take the first question. So for the first question says the free running frequency of a VCO is the frequency at which the VCO operates when the control voltage is zero, the maximum frequency that VCO can generate, the minimum frequency that VCO can generate, and the average frequency over the entire voltage range. So in VCO, like I said, the output voltage, output frequency is a function of the input voltage. So the out, but yeah, it is not a zero function. Means it does not go to zero when the voltage is zero. So the frequency output, the free running frequency is defined as the frequency at which the voltage input is zero. So Vin equal to 0. So if you give no input, then also because this is an oscillator, it will have a natural frequency response. So it will have a natural oscillation frequency even without any external stimulus. So that is called the free running frequency. So when Vin is equal to 0, means there is no external stimulus, the voltage control oscillator directly gives an output called F naught, where F naught is the free running frequency, is the free running frequency of VC. Now, if F out equal to F naught is the free running frequency of the VC, then it is option A. The correct answer is option A. Okay. Now, the relation between the free running frequency VC and the control voltage of a PL. So now we have to go deeper into something called a phase lock tree or PLL. So a PLL is basically a particular loop circuit which has a VCO inside it, and what it does is it tracks an external frequency. So if you give it some external frequency or conversely some external phase as an input, it will create an output which will be approximately equal to the frequency or phase of the input. So it is constantly tracking the frequency or phase of the input. In its most basic configuration, a phase lock loop compares the phase of a reference signal to the phase of an adjustable feedback signal. There, okay. So here, what happens is that the phase is adjusted via an error detector, a loop filter, and a VCO. So this is a basic PLL configuration. So what happens is you give a particular reference signal. That reference signal, the difference or the error from the previous output is calculated. Then that is amplified. So this is the error detector. It amplifies the error. So after that, you filter that error and you generate a frequency called a frequency of oscillation corresponding to that error. So a phase lock loop control system whose output signal phase would be is fixed related to the phase of an input signal. So it keeps close track of the phase. So here, and it's okay. So here it is synchronizing with respect to the input phase. So we will now look into the implementation of a phase lock loop. So what is this used for? This is used for creating a frequency that is nearly equal to the frequency of a reference or standard signal. So if you want to create a particular frequency at a particular for a particular signal, so you can have a reference signal, and from that reference signal you can create that particular frequency. So it is a feedback system in that the error is filtered, and then a frequency corresponding to that error is generated, and that error or that output rather is fed back, and the next stage's error is dependent on that input and the previous stage output. So here you have V1. So here you have V1, a voltage. So this will get compared with something that is V input. So this is Vi1. So it will be compared with V0 0, and we will have E1. So the previous output and the new input. So E1 is Vi1 minus V0 0. So in general, En is Vin. Now the En plus 1 is Vin n plus 1 minus V0 n. Now with this configuration, this error is how do we get from this error to the next step. So we know how the error is calculated, but how do we get from error to the output voltage? There we use a loop filter. First, before that we use a constant gain amplifier. After that we use a loop filter. So the next part is the loop filter. So the phase detector will compare the reference signal with the oscillator frequency or the VCO output. It will compare the VCO output with the input signal, and it will give an error signal. That error signal will be amplified by a constant gain amplifier, and then the loop filter, which is usually a low pass filter, generates an error voltage from that error signal. So basically we need a particular frequency response of that voltage, so we cannot guarantee that with an error signal. So what we have to do is we have to further filter the error signal so that we get the error in the error signal in the desired bandwidth. Now after we have restricted it to a desired bandwidth, we will get the error voltage, band restricted error voltage from that low pass loop filter, and from there we will use a VCO to generate the input frequency, at the output. So the VCO then increases or decreases the oscillator frequency to lock to the input frequency. So now since the VCO frequency is a function of the input voltage, so according to the error it will create a frequency. So after filtering, it will modify its frequency, not create, rather modify. So after filtering, this one becomes EF. Say now this EF is passed through a VCO, and finally the VCO output is fed back. So the VCO output is V0. Now this EF, the frequency of the output, will be directly a function of EF. So this EF are the delta. So the change in the frequency will be directly a function of the error function of the error voltage. So we can have, whenever the voltage changes, we can have such that whenever the voltage changes, so we were talking about phase lock loop. So whenever the voltage changes, we have an error signal corresponding, and that error signal will create a error frequency, and that error frequency is modified. Error frequency is modifying the actual output frequency so that we can keep track of the input frequency. This is how a phase lock loop works. Now coming to the next question. The relation between the free running frequency of VCO and control voltage of PLL. So now Now in VCO, the free running frequency is the frequency generated when voltage is 0. And thus, when this input voltage will be 0, when will VCO output the error frequency? The VCO will output the error frequency when VCO outputs free running frequency when error equal to 0. Now we will come to the next topic, that is the control voltage of a PLL. So we have to find the relation between the free running frequency of VCO and the control voltage of a PLL. So the next topic will be to understand the control voltage of PLL so that we can compare it with the PLL. So the control voltage of the PLL is basically the error that is filtered. So EF is the control voltage. Now they are asking what is the EF. Here is the control voltage of the VCO. So EF is the control voltage because it is outputting frequency that is directly proportional to the control voltage error filtered error. So control voltage of VCO or PLL, sorry, control voltage of PLL is VCO input, that is filtered error. So the correct answer is linear because we see that this error filter is the as the control voltage of the filtered error voltage increases, the frequency of the VCO will increase, and if the control voltage decreases, it will decrease. So it is a linear relation. So the next, so today the relation between the free running frequency of VCO and the voltage control voltage in PLL is linear. The next question is that which components are typically used in first order loop filter in a PLL. So in a first order loop filter, so filter is mostly implemented using RC circuit, LC circuits. So filter RLRC circuits, and but the oscillator is implemented using LC circuits. So here, what the mostly RL and RC, among that mostly for filters RC is used. So RC is resistor and capacitor. So for a first order filter means the filter transfer function will be 1 by 1 plus SRC. So this is the first order filter, and it is a low pass filter. So it is one resistor, one capacitor, like this. One resistor, one capacitor. This voltage is V out, and this voltage is in. Next is consider a PLL with the following specifications. The input voltage signal is sin theta t. Output of the VCO is yt equal to 2 cos theta t, and the constant of the VCO C equal to 1, and its free running frequency is omega c. So the input signal is xt equal to sin theta t, and the output of the voltage controlled oscillator is yt equal to 2 cos theta t. The constant of the VCO is 1, and its free running frequency is omega c. Assume that the transfer function of the loop filter is 1, and the phase error is theta I minus theta t. Theta I minus theta naught t is small. If the input phase is omega ct plus phi naught, then the steady state error limit. So we have to find this theta et, we have to find the value when t goes to infinity of this error. So this is the steady state error. So here the so now we have to do something called small phase error. Since the phase error is small, so we have to do something called the small phase error analysis of PLL. So now we have to do something called a small phase error or small signal analysis of the function PLL. So So for the small phase error analysis, we have to assume that sine theta is theta, and will that will enable us to have a linear relationship between the which will linear relationship between the frequency output and the voltage input, so that we have the nonlinear behavior of the PLL approximated as a linear system. So for a small phase error analysis, the value, the transfer function of the error in phase, the transfer function of the error, rather the value of the error in phase in Laplace domain is given by this function. So when theta et is very small, then sine theta et is approximately theta et. This leads to the linear relationship between phase or frequency of output with input voltage. So the first order phase response is given as theta s is equal to s by s plus akh into plus phi naught by s. Now this is the s domain representation. Now we have to find the steady state value. So we will use the final value theorem, that is limit t tends to infinity theta et is the same as. Now first we have to learn what is akh. So a is the amplitude of the signal. This is the amplitude of the signal. Omega c is free running frequency. Free running frequency. Omega naught, phi naught are input frequency and input. This is phi naught is input phase, and what are k and h? Well, k is the VCO. K is a function that is related to the VCO constant, and h is the transfer function of the loop filter. So a is the amplitude of the signal, k is the gain of the VCO, you can say gain of the VCO, and H is the gain of the loop filter. Gain of loop filter. So the gain of loop filter is given to be 1, and the amplitude is given to be 1, and K, which is the gain of the VCO, is half into C into amplitude of output. So K is half C, where C is the VCO constant, which is 1, and B is the amplitude of output, which is 2. So K is also 1. So K is 1, A is 1, and H is the gain of the filter, which is also given to me 1. So it is just 1 into 1 into 1. And this one is omega naught minus omega c. So this is just plain 1. This is omega naught minus omega c by s square. This phi naught by s. Now what is phi naught? Phi naught is the input phase. So the input phase is clearly given to be 0. So again this is 0. So finally we have theta es as s by s plus 1 into omega naught minus omega c by s square. So omega naught minus omega c by ss plus 1. Now limit theta tends to infinity, theta es, sorry, limit t tends to infinity, theta et is limit s tends to 0, so the phi naught omega naught and phi naught are the frequency and phase. So here omega naught is equal to omega c, slight mistake here. So here omega naught minus equal to omega c. So this will not go to 0. Rather this will go to 0 because omega naught is equal to omega c. This phase, this signal, particular signal, as pure phase. This particular signal has pure phase. So omega naught minus omega c is 0. So here you have limit t tends to infinity, theta et is limit s tends to 0, s theta es. This is the final value theorem. So here this, you will have phi naught by s. So instead of this you will have phi naught by s plus 1. So ultimately what you have is limit s tends to 0, s into phi naught by s plus 1. So if you put s equal to 0, you will get 0. So at steady state, the error is 0. So we can say that at steady state, it achieves perfect throughput, and the difference between the tracked voltage and the actual voltage becomes 0. So the answer is 0. For the same PLL circuit described, if theta it is omega c 1 plus delta t. So previously theta it was omega ct plus pi. That's why omega naught was equal to omega c. But now it is theta it is omega c plus delta omega c. So it is slightly more than the natural free running frequency into t. That is, you can write as omega c 1 plus delta into t. So it is the frequency is slightly more than the free running frequency. Now, correspondingly, the the first order response of this will be theta es is s by s plus akh. Akh are all identically 1, so this will be 1 into omega naught minus omega c by s square plus phi naught by s. Now phi naught is equal to 0, so this becomes 0. And omega naught is omega c into 1 plus delta. So ultimately what you have is s by s plus 1 into delta omega c by s square. So what you have is delta omega c whole divides s into s plus 1. Now theta t limit t tends to infinity is equal to limit s tends to 0 s theta es. So you have limit s tends to 0 s theta es means you have delta omega c by s plus 1. So it is ultimately delta omega c. So we see that when the the frequency of the input is slightly different from the VCO frequency, then also it is perfectly free running frequency, then also it is perfectly tracking the difference in the frequency. So when it is omega c, when the input frequency is equal to the free running frequency, the difference is 0. And when the input frequency is slightly higher or lower than the input frequency, then that amount of error is constantly maintained throughout the time, like at steady state, throughout the steady state. So we can say that at steady state we have a explainable output that whatever was the difference of your frequency, exactly that from the free running frequency, exactly that is reproduced at the output. But if your phase is not small, then this small phase analysis does not hold true. Phase difference is not small. Then this small phase analysis will not hold true. So this will hold true only when delta is very small. If delta is very large, then the phase difference will not be small. So we cannot apply this mode. So delta has to be very small. So the correct answer is omega c delta. Now, for the same xtyt given in question 4, assume the input phase theta it equal to 2 into 10 to the power 60 and the free running frequency of the VCO to be 10 to the power 6. Assume the VCO constant to be 2 into 10 to the power 6. Note that the small phase approximation can no longer be applied if the initial phase error is phi E naught equal to pi by 12, then the equilibrium value of phase error. So here the difference between the free running frequency, here the omega c is 10 to the power 6 and omega naught, the frequency input frequency is 2 into 10 to the power 6. So the difference omega c minus omega naught minus omega c, that is equal to 10 to the power 6. So that is huge. So we cannot apply the small pair approximation analysis. Thus, we will have something called the large error analysis of PLL. So, large error analysis of PLL gives us a differential equation that is given as this gives us a differential equation d theta e dt is equal to omega naught minus omega c minus sine of the input, sine of the error bits into 80 sine theta 80. Now AK is 1, so d theta e dt so this is 1, so it's just no, sorry, the k is now not equal to, the k is half into 10 to the power 6 into 2 into b of the output amplitude is 2, so this k is 2 into 10 to the power 6, so ak is 2 into 10 to the power 6. So now we want to find the equilibrium value, that is, we want to find when d theta et d theta e dt is 0. That means it has reached equilibrium. Implies here omega naught is 2 into 10 to the power 6 minus 10 to the power 6 minus 2 into 10 to the power 6 sine theta et equal to 0 implies sine theta et equal to half, or theta et is 2n plus 1 pi by 6, odd multiples of pi by 6. So the equilibrium point, first equilibrium point is at n equal to 0, that is pi by 6. So the first equilibrium value is at pi by 6. So the correct answer is pi by 6. You put n equal to 0 into n plus 1 pi by 6 and you get pi by 6. Now, again for the same circuit, assume the VCA constant is 0.5. Now, assume VCA constant is 0.5. So we repeat the calculation. repeat the calculation, but k is this time k is half into 2 into half into 10 to the 6. This is c, this is b, and this is half bc. So ultimately you have half into 10 to the power 6. So k is half into 10 to the 6, and this is omega naught minus omega c is 10 to the 6. So 0.5 into 10 to the 6 into sine theta 80. Now for equilibrium, sine theta 80 is equal to 2, which is therefore which is not possible. Therefore equilibrium does not exist. The equilibrium simply does not exist. Now again with the same circuit, this time the transfer function of the loop filter is s plus 1 s plus 1 by s square, and the input phase is delta. So again we are going back to small phase error analysis because delta is very small. So we are going back to small phase error analysis. So this is small phase. This one was large phase. This one was again large phase. So we are back to small phase analysis. You can take your time and try this one. After your attempt, I will try to solve. I will solve this for you if you are unsuccessful. So please take 3 minutes and try to solve this because this has already been done previously. So I hope you will be able to solve it this time. So now we will take on the small phase analysis in this question. So the theta input phase is omega c plus delta omega c. So the small phase analysis equation is for PLL is given as the error theta e and s domain or Laplace domain is s by s plus akh into omega c minus omega naught by s square plus phi naught by s. So here we will put we know that a is 1, so we will put a equal to 1. Other things remaining constant, a is also 1, but h here is s plus 1 whole by s square, so it is s plus 1 whole by s square. So theta es becomes, and omega c is equal to omega naught as theta I t, as theta I t, the input phase is omega naught t, omega ct plus phi naught. That's all. So theta es is s by s plus 1 की जगह s by s plus 1 by s square whole into phi naught by s. So this s and this s will cancel. So it is s square phi naught by s cube plus s plus 1. So now in this problem we have to find the steady state phase error value using the final value theorem. So limit t tends to infinity. Final value theorem is theta et is limit s tends to 0. S theta es. So we will just put limit s tends to 0. S into s square phi naught by s cube plus s plus 1. So if you put this, the answer will come 0. So the correct answer is 0. There is no steady state phase error. But since the loop filter is not all pass, here we have a low pass loop filter, so we see that the steady state phase error is 0. So even the phase that was previously, it is the phase that was previously omega c plus delta omega, it is tracking that perfectly given enough time steps. So a low pass filter is more preferred for loop filter. Now, which of the following function module is not required in Costas loop? So now we will go to Costas loop, the next part of our assignment. What is a Costas loop? So Costas loop is designed from a PLL only. So what we do is we use it as a demodulator. So we try to recover the carrier frequency from the suppressed carrier modulation signal like DSBSC. So when there is a full carrier modulation, you can easily filter out the carrier. But when there is a suppressed carrier modulation, filtering out the carrier is not that easy as filtering, because the carrier frequency component is actually 0. So from the side bands you have to infer the value of the, from the side bands you have to infer the value of the carrier frequency. So it was so here, so we can, from sitting at the receiver, we can directly estimate what the carrier frequency of the transmitter was, even without transmitting carrier frequency. So this was a path breaking revolution, because in digital communication, because it allowed estimating carrier frequency, Costas loop, Main function of ghost sleep is estimating carrier frequency without actually sending carrier frequency signal. This is ghost sleep. So we are saving the power of transmitting a carrier frequency as well as getting all the information that is needed. So here we have a VCO and we have a filter and we have loop filter. So we have two different kinds of filter. One is a normal low pass filter and another is a loop filter. So it has a VCO, a low pass filter, a loop filter. Now what happens is this modulated signal is tracked with a VCO. So the modulated signal is tracked with a VCO, which generates sine omega t. That sine omega t is multiplied and demodulated. So this is a classic demodulation. See, here we are having, by using the VCO, we are generating sine omega t. We are multiplying it with a modulated signal and we are getting back the message signal. So this is a classic demodulation structure. In quadrature also we are doing the same. Now we are multiplying with cos omega t and we are getting back the filter. Now the difference between these two is fed to a loop filter, and that loop filter, from there the output is fed to a VCO which generates the carrier frequency. So this error is what is generating the carrier frequency. So ultimately, like that, we get the carrier frequency at the output of the VCO in the locked state. So when the VCO phase locks onto the modulated signal, we get the carrier signal as output. So it has multipliers, low pass filter, loop filter, and VCO. It has 4 components. So low pass filter, PLL, the entire thing is a PLL, and there is a phase shifter, and there is a phase shifter because there is sine omega t and there is cos omega t. So of course there is a phase shifter to generate both sine omega t and cos omega t. So there is a phase shifter, there is a PLL, there is a low pass filter. What is not there is a band pass filter. So the correct answer is option B. Okay, the correct answer is option B. Now phase lock circuit is only used for frequency phase tracking, not frequency tracking. Now you see, the name implies phase lock loop, so it is locking onto a phase. But what is phase? Phase in normal circumstances is theta t equal to omega naught t plus phi naught. So if you differentiate the phase, what do you get? You get frequency. So you see, when you are tracking phase, if you do a derivative of the tracked phase, what you get is the tracked frequency. So this is our, so if we track phase, we can equally well track frequency. So the correct answer is false. Phase left loop can be used to track both phase and frequency. Now we come to the so we have completed phase lock loop, Costas loop, and voltage control oscillator. Now we will see some additional MCQs on these topics. So in a PLL, capture range is equal to lock range is not equal to free running frequency. So capture range and lock range. So what is the capture range and lock range of a VC or a PLL? Capture range, lock range, and free running frequency. So free running frequency is the exact frequency at which the voltage is zero. The capture range is the range over which the of input frequencies over which the PLL will capture the input signal. So it will track the input signal completely. So it is lock range is the tracking range where the range of frequencies of the PLL system follows the change in input frequency. So in the lock range, it locks onto the frequency, but there is a steady state error. So there is a steady state error, but it eventually locks onto the frequency. So even if there is a difference, the frequencies are maintaining a constant difference. So it is kind of tracking. So if your input frequency changes, the output frequency will change by the same amount. So there is a difference, but that difference is constant. That is the locking. So in locking, input and output frequencies or input and output phases can be different, but so in locking, output phase and input phase maintain a constant difference at steady state. Output phase minus input phase is equal to constant at steady state. Now another is capture or capture. In this, output phase is exactly equal to the input phase. So it is not just locking into the signal, it is capturing the signal completely. So that is the capture range. So the capture range is smaller than the locking range. So capture range is less than locking range. This is the correct answer. Next, we have the voltage controlled oscillator is uh, VCO. This is a silly answer, of course. That is just the abbreviation of voltage control oscillator. Next is it is a voltage to frequency converter, which is true. It is a voltage to frequency converter. It takes input voltage and gives output frequency. So the correct answer is all of the options. Okay. So voltage, yes. So what are the applications of a voltage control oscillator? In FM transmitter, a voltage control oscillator is used to vary the frequency of carrier signal. So basically, in frequency modulation, what you do is according to the message input message MT, you change the frequency of the carrier. Now this is a classic VCO or PLL experiment. So you are changing a frequency in accordance with a voltage. That is the classic application of VCO. So it is used to generate FM signals. And PLLs. So PLL is again used for signal demodulation and recovery, and that is VCO is a key part of that PLL. And next is VCO is a function generator. That is, it generates different harmonic frequencies according to the input voltage. So it can be used to generate various functions. As a composition of the harmonics, it can be used to generate various functions like sine wave, square wave, and triangular wave. Next, how is oscillation frequency controlled in voltage control oscillator? By the input voltage. Next, output frequency of the VCO is inversely proportional. So, output frequency of the VCO is inversely proportional. It is output frequency is direct in proportion to the voltage usually. But what is it inverse in proportion to? It is inverse in proportion to the resistance and capacitance, because the resistance and capacitance form the gain of that filter, loop filter. And if the resistance and capacitance is more, then if the resistance and capacitance is more, so just wait a minute. Okay. So output frequency is the loop filter is 1 by 1 plus SRC if it is a first order PLL. Now this Hs, if you do small signal analysis, then this loop filter value, the gain value will be low, so the output frequency will be smaller. So it is A and B. Now, voltage control oscillator frequency is directly proportional to input voltage. What is VFC? VFC is the voltage frequency converter, and in how many groups voltage control oscillator are characterized. So here there are two different types of VCOs. So based on the frequency generated, one is the harmonic oscillator, which generates sine. Harmonic oscillator which generates sine or sinusoids, and another is the relaxation oscillator which generates triangular waveforms or sawtooth. Okay, so VCOs are either harmonic or triangular. So two types, harmonic and triangular. And next, what are the various types of VCOs? A, harmonic; B, relaxation or triangular oscillator. So VCOs are of two types. One is harmonic oscillator, harmonic oscillator, which is sinusoid, and another is a relaxation oscillator, which is a triangle. So next question is, what type of oscillator generate harmonic? Sinusoidal, that is harmonic. And harmonic oscillator consists of an amplifier and a resonator. And harmonic oscillator is an LC oscillator. So what is the formula to calculate obtained frequency and the output in voltage oscillator? So the output voltage will be the output frequency will be a function of the voltage, and it will be a function of the RC. So here you can just do a direct dimension analysis. 1 by RC has the same unit as, since RC is the time constant, 1 by RC has the same unit as frequency. So these two, B and D, B has the units of voltage, D has the units of nothing, it's unitless, dimensionless. So B and D cannot be the answer. Now what is the answer, a dimension of C? C is voltage into frequency. The dimension is voltage into frequency, which is again not appropriate. And this one has a dimension, the voltages get cancelled, so that it has a dimension of frequency only. So by dimension analysis only you can tell that the correct is option A. As you can see, it is inversely proportional to RC and directly proportional to the voltage VC. And crystal oscillators are harmonic oscillator, relaxation oscillators. Harmonic oscillator, sorry, not relaxation oscillator. And relaxation oscillator generates triangular or sawtooth. And what kind of oscillators are utilized in integrated circuits? Integrated circuits must use relaxation oscillators. Okay. So what is the purpose of a voltage control crystal oscillator? Is that it adjusts the operating frequency. What is the purpose of voltage control crystal oscillator clock generator? It generates timing signals because it is a clock generator. So it basically mimics the clock frequency and generates a timing wave, square pulse wave. What are the design parameters of voltage control crystal oscillator generator? So one is the frequency tuning range, that is the frequency, and then there is a center frequency, that is the free running frequency, and then there is the tuning voltage range. Okay, so how is frequency controlled? How is frequency control achieved in VCO? By using timers, varactor diodes, counters, or multiplexers. So it varies the resonant frequency of the tank circuit. Tank circuit here means LC, inductive capacitive circuits. So it uses varactor diodes to control the resonant frequency of the LC circuits. What determines the tuning range of a voltage control oscillator? So tuning range means basically the input voltage tuning range. Now the input voltage depends on the load variation and the resistance, the capacitance, and the feedback. So the correct answer will be capacitance. Now, what are the various applications of voltage control oscillator? Communication system, radar, and phase lock loop. It is used in all of them. It is used in radar to track the target frequency and target phase. It is used in communication system for frequency modulation, and it is used to make phase lock loops, which have applications of its own. And how the output frequency in voltage controlled oscillator are changed. So voltage control oscillator, the output frequency is a function of the voltage and RC. So voltage, resistor, and capacitor. So monolithic function generators are voltage controlled. So if you want to generate a function, what you use is VCO, and VCO is voltage controlled strictly. So what are the various applications of voltage control crystal oscillator? So here we are not tracking a frequency, we are generating a frequency. So that can be used in TVs, modems, and computers, all of them. So voltage controlled oscillator are used in frequency modulation, frequency shift keying. So both of them involve varying the frequency in response to the input voltage. In frequency modulation, you vary the frequency continuously in response to the message signal or voltage, and in frequency shift keying, you vary the frequency in discrete steps. utilized. Mm. Mm. Which device is utilized in diagnostics and recording? So it will be voltage control oscillator. Viot converts lower frequency signals to audio range. Here again you have VCO. VCO can convert lower frequencies into audio frequency range by tracking audio reference signal and bringing the frequency of the voltage signal to that tracking frequency. So that is how you convert it into audio frequency, convert the voltage into audio frequency. So that will be all for today. Thank you. Have a nice day.